Hey guys, so in this example we have a weird arrangement of objects that are sort of hanging together by a bunch of ropes and rods, and we want to find the missing masses. So we don't know the mass of A and C. We're going to call this guy B, and we're going to say the mass of B is 4. So we want to find the masses of A and C. And we also want to know all these tensions, right? We want to know all the tensions. So calculate the tension of the 5 ropes and the 2 missing masses. It says that the system is in linear and rotation equilibrium. This means that sum of all forces equals 0. This means that sum of all torques equals 0. It also tells us that all the ropes, all the vertical ropes, which are the arrows, are massless, and all the horizontal rods, which are the horizontal lines, are massless as well. So we don't have to worry about those. And we're going to use G as 10 meters per second squared to simplify things. All right, so first of all, I want to name a few things here. We have A, B, and C. Now this is going to be the tension of C because it holds C. This is going to be the tension of B because it holds B. This tension here, I'm going to call this the tension of B and C because it holds those 2 masses. This is going to be TA. Whoops, that doesn't go there. This is going to be TA. And this one holds A, B, and C, so this is going to be TABC. Let's talk about forces first. All the forces cancel, so let's look at each object. This here has a force of mBg, and because this object is in equilibrium, the tension up cancels with the force down. I can actually calculate mBg because I have the mass is 4, gravity is 10, we're using 10, so this whole thing is 40, therefore this has to be 40. Here, I can't tell what TC is yet because I don't know MC. So we're going to have to use something else. If I look at this dot here, you can tell that this dot is being pulled up by TBC, but pulled down by these 2 guys here. Okay, so TBC is going to be TB plus TC. If you look at A, I have MAG, but I don't know what that is yet, so I can't find TA just yet. I can also see how TABC is TA plus TBC. That's why we call it ABC, because it's all 3 of them. Okay, so there's a bunch of stuff we don't know yet. We have to find these 2 masses, which will allow us to find these 2 tensions. And then once we have that, we're missing this. That's why we can't find this. And then once we have that, we'll be able to find the whole thing. We're also missing all of this stuff up here. Okay, you want to start this problem from the ends of the problem. What I mean is this is like a bunch of masses that are chained together. This is the lower point, the end of the problem. The reason I call it the end of the problem is because we're going to get to this point, we're going to need this point first. And A will contribute, and then this stuff will contribute as well. So the first thing we have to do is work our way from the bottom here up, right? And then once we get to this point here, we'll be able to figure out what A is. All right, so let's just get started. So everything's figured out for B, so we're gonna go with C. We can't figure out C using using the sum of all forces equals 0 because we already did that. All that tells us is that TC equals MCG, but I don't know these 2 guys, so I'm stuck. So what you have to do is you have to use torque. And you're going to have to say, we're going to say that the torque about this point here, let's call this point 1, the sum of all torques about point 1 is 0, which means that all the torques acting on it will cancel out. There's 2 torques acting about that point. First of all, TB is doing this. So this is torque of TB. And TC is doing this, torque of TC. So imagine you're the center point. There's a rope that pulls you down this way, and there's a rope that pulls you down this way, right? And those 2 torques will cancel. So I can write TB equals TC. Now, a torque is a force, which in this case is TB. The distance, which we're going to call RB, and then sine of theta B. And I'm going to write the same thing for the right side, TC RC sine of theta C. The R vector would be this here, right? From the axis, this is the point we're treating as the axis of rotation, to this point here. So this is RB, and this is RC. Notice that in both cases, the axes are this way, the tensions are down. So in both cases, the angles are 90. So this is going to be a 1 and a 1. So this simplifies to TBRB equals to TCRC. And by the way, that's going to be the case with every one of these kinds of points. So when you go here to point 2, we're going to be able to write the same thing. There are no angles here for us to worry about. All right. So I know that TB is 40. RB is the distance. It says right there. The distance is 1. Then I'm going to be able to find TC because I have the distance here for RC is 2. So TC equals 40 divided by 2. TC is 20. Okay? TC is 20. So now that I know that TC is 20, I can plug it in here. 20 equals MC 10. That means MC is 2. Okay? So not only we figured out the tension, but we also figured out that MC will be 2 kilograms. Okay? Now, there's a faster way you could have done this once you get good at this stuff. It's basically a little game. Once you realize that this is the relationship, you can sort of say, hey, you know what? This guy is, this guy here is, whoops, C is twice the distance. So to have the same torque, you have to have half the mass, right? Because torque, in this case of the weights, is mgr, and here the sine of theta just gives us 1. So if you have double the distance, you have to have half the mass in order to have the same torque. Okay? Double the distance, half the mass. Cool. Now that we know TC, we can actually find TBC, right? TBC is TB, which is 40 plus 20, 60 newtons. Okay, 60 newtons. Now, check it out. You can think of this tension right here, as essentially holding the 4 and the 2, right? So you can think of this as A and 6. You can combine those two, the 4 and the 2, into a 6. And then there's a tension here. This is 1 and this is 4. And remember what I just told you? If you are farther, you have to be lighter. A is 4 times as far from the central point here, from the axis of rotation, from the support point, than 6. So if it's 4 times farther, it also has to be 4 times lighter. And just by using this, you can tell that the mass of A has to be 6 over 4, which is 1.5. So you can do it like this very quickly. All right? Now, I'm going to do this the full way, which would be to write, here we wrote that all torques on point 1 are 0. Now I'm going to write that all torques on point 2 are 0. And what this gives us is that the torque of A will cancel out with the torque of BC. Torque of A equals torque of BC. So tension of A, RA, sine theta A equals tension BC, RBC, sine of theta BC. We just talked about earlier how the sines will just be 1 because all the R vectors are horizontal and all the tensions are vertical. The tension we're looking for here is A. The distance is 4 meters, so TA 4. TB is 60. The distance for TB is 1. It says right here, 1. So TA is 60 over 4, 15 newtons. So we know that this is 15 newtons. And these two guys have to be the same. So if TA is 15, then MA, gravity is 10. MA is 10 divided by 15, 1.5, which is what I just mentioned here. But I wanted to show you how this stuff works out, okay? So you can actually skip some steps if you just realize that you have this relationship here at any one of these points that connect stuff, right? You can write, you can actually also write this like this. MBRB equals MCRC, which is essentially what I did when I shortcutted this question. The reason you can do this is because the torque equation does this. MBGRB equals MCGRC, and then you're essentially canceling the R's and ending up with something simpler like this. Okay, so that's a quick shortcut you can use. I almost have everything. The last thing I have to do is I have to combine the 60 here with the 15 here, and I get a 75 newtons as the tension of everything. So I got the masses. The masses are 1.5, 4, and 2. The tensions are 75, 15, 60, 40, and 20. Okay? And all it took was using the fact that the tensions up equals the masses, the weights down, and the fact that you can use torque about points 1 and 2, the fact that the torques cancel, and you end up with stuff like this and stuff like this that allows you to find the other ones. Okay, so it's a very peculiar kind of question, but once you get the hang of this, it's really easy to solve a bunch of them. So hopefully it made sense. Let me know if you guys have any questions, and let's keep going.